This is the assignment that's called Force Diagrams. Force Diagrams number 3. Oh, never mind that. These are similar to a lot of ones that we've seen before. We're just going to have more practice, because practice is good. So here we got an object that's slowing down. If things are speeding up or slowing down or changing direction, those are all changes in velocity. So that means the forces are not balanced. So if it's going this way but slowing down, that's like if you needed to do that in broom ball, you'd have to tap this way. So there must be some unbalanced force that way. So let's see, there's my block. I'm going to have the ubiquitous force of gravity on the block from the entire Earth. I'm going to sharpen this pencil real quick. Be right back. Oh yeah, there we go. So force of gravity on the block from the entire Earth, and then I've got a normal force on the block from the what is it, a table? I don't know what it is. The floor, I don't really care what you call it. I'll say it's a table. And then there's this force of friction on the block from that same table. Those are equal to each other, and that's unbalanced. That's what's slowing it down. Here's an object that's sliding without friction. So it's going this way, so that means I'm going to need my axes to be all tilted like. So here's my force of gravity on the block from the, how about a ramp this time, whatever it is. And now I'm going to tilt my page so that looks horizontal, make my other axis, make my X and Y components of this, just like I'm plotting a point. You can use graph paper if you want for these. Let's see, there's no friction, so that's not anything happening here. There is a support force, which is always perpendicular to the surface. That's why we make our axes, one of the reasons we make our axes this way. Normal force on the block from the ramp. And that is it. That balances this, and that, since there's no friction, it's going to be speeding up because this little bit is unbalanced. Static friction. Static just means not moving. Just going to extend that and drop gravity straight down because gravity doesn't care. Force of gravity on the block from the ramp. And then tilt page, draw a perpendicular axis, support force, which we call the normal force, on the block from the ramp. And now this one's not sliding. There's a force of friction there on the block from the ramp. And if I make my components, which just means like X, Y, just like I'm plotting a point, that must be equal to that, and this must be equal to that. Everything's balanced. Cool. Object is suspended from the ceiling. Now, if this was moving, I guess it would probably fall straight down, so I don't have to do any tilted axis stuff. It's just straight like that. You can draw them in if you want. I don't think I would complain in this one, or other very simple ones like this, if you just made your up and down force and didn't do the axes. That'd be okay with me. Force of gravity on the block from the entire Earth. And then I've got, try not to call this a normal force. It's not. This is a force of tension on the block from the string. Strings don't do normal forces, they do tension forces. And that thing's just hanging there, not moving, so those forces are balanced. Here's an object suspended from the ceiling. If it were going to move, fall straight down. I guess you could say, well, if this one was cut, then it would like swing over to the side. Yeah, that's, it's just complicated. There's no ramp or anything, so let's not make things worse. Now I've got two tension forces, one like this and one like this. Now how could those three be balanced? Well, because there's no ramp, my axes are just regular old XY, and anything that's pointing into one of the quadrants is going to have to get broken up into its components so that we can see how things balance. So this plus this, those two ups would have to equal this down. So if this was 3 and 3, then that would be 6. And the left and the right, those are going to balance each other. So I can't do there's no geometry trick to show that those are equal to this. I just leave them. Eventually, when we have numbers, we can, write an equation or something. All right, how about this? This is, if you didn't figure out what this is just another string holding this that happens to be horizontal there. So the idea here, again, there's no ramp or anything, so this is just a regular vertical and horizontal axis plan. Force of gravity on that block from the entire Earth. And then I got a tension force this way, force of tension on the block from this rope or string, whatever it is, and then I got another tension force from that other rope, and then this is pointing off into one of the quadrants, so that needs to be broken up into its component parts. And so then left and right can balance like that, and up and down can balance. And I can use my tick marks here because I just have 1 and 1, 1 and 1 balancing each other. All right, cool. Object is motionless, no friction. And so I got a string. I think we did one just like this. Remember that person on the hillside, and there's a rope tied around their waist or something, and tied around a tree so they weren't sliding down. This is the same exact situation. So force of gravity on the block from the entire Earth, and I'm going to tilt. And I'm going to have a support force, and I'm going to have a tension force. I call that the support force, support, normal, same thing. That's on the block from the, what do I call that, a ramp. And this is a force of tension on the block from that string or rope or whatever you want to call that. And now this is pointing off into one of the quadrants, so if you've started to figure out every time we have a ramp involved, that gravity is the thing that's going to get X wide like this, you're right. That's what's going to happen every time. There we go, balanced forces. And this, we did one like this too, with a little like book on a shelf thing. So let's see. Got the force of gravity on the block from the entire Earth. Everything else is going to be in line with our new axis system. So I got a support force here, and I got a support force here. So those are normal forces. Normal on the block from the wall of that, whatever you want to call that, and normal force here on the block from the, I'll just call that ramp because it's consistent with the other ones. Again, exactly what you name these things doesn't matter too much. Of course, the entire Earth, you would not want to confuse us with another planet. All right. How about this? Object is pulled by a force parallel to the surface. Unfortunately for you, I did not specify here whether there's friction or not, and whether it's being pulled at a constant velocity. So let's say, for just the sake of argument, that is a constant, not constact, that's not a word, constant velocity. That means the forces are balanced. So, no ramp here, so regular axis system like that. So I got the force of gravity on the block from the entire Earth. I have a normal force. You know what they call the normal force in France? Le force normale. Normal force on the block from the floor. How about? Not sure what it's getting dragged across here. Those are balanced. And then I got the force of pull on the block from, I'm not sure what's pulling it, so I'm just going to say puller. Maybe it's you, I don't know. And force of, if it's going at a constant velocity and the forces are balanced, there must be a force of friction here on the block, also from the floor. How about this? Object is pulled by a force at an angle to the surface, right there. Now, should I make my axes like this, since that force is up like that? No, because what direction is this moving in? It's moving this way. So the axes are always going to line up with the direction of motion, or the direction of like most likely motion, if there was. So let's see, you got the force of gravity down on the block from the entire Earth. And then I've got this pulling force. Now that's going off into a quadrant. This is force of pull on the block by the puller. You think it's the same puller from number 9? I wonder. Like they're a serial puller. They just go around pulling on blocks. Okay, so that's going off into a quadrant, so that's the one that's going to have to get broken up into its XY components. And then if we think about like what else is going on in the up direction, does this balance this? Well, no, there's also a normal force. I'm not going to make it look too big. It wouldn't be as big as this, because this and this, the two ups, are going to balance that down. So I have force of normal on the block from the, what did I say in the last one? Floor? Oop, we'll say table this time. Whatever. And then the only other thing, since this is it's being pulled, we're also going to assume constant velocity, because that's really the focus of this unit, is balanced forces. So this is a force of friction on the block from the table. These two I can say are equal, but in this case, the ups and the downs, I got up plus up equals down, so those aren't equal, not in a way I can show with tick marks. Right? All right. The object is pulled upward at a constant speed. Constant speed, forces are balanced. Now you might see this and be like, okay, there's that downward force, but we're making a force diagram for this object. And that object does not know that there's a pulley there. All it knows is there's something pulling up on it. So that whole downward force in the pulley redirect thing, that block doesn't know about it. It doesn't really know anything because it's a block. But point for us here is that if we're just doing the forces on the block, then we're just looking at the block and like ignoring the rest of what's going on. So there's a force, it's some kind of rope, so I'm going to call that a tension force on the block from the rope, and that's it. Now, if you wanted to make a force diagram for the pulley, that's a whole other thing. That's actually pretty complicated, a little bit beyond what we're going to do. Point here is just to Make sure you're focusing, isolating that object. How about here? This is kind of like number 10. Excuse me. I'm going to make it down here. Now, it's moving this way, and I'm going to assume, again, that this is constant velocity, which means the forces are balanced. There's my block. So, of course, there's the ever-present force of gravity on the block from the entire Earth. Then I've got this pushing force down like that. It's a force of push. And on the block, the pusher. Uh-oh. That's what people who sell drugs are called, pushers. So, let's see. Here, since this is going down into one of those quadrants, I'm going to have to break that up into the x and the y coordinates. Excuse me. So now the support force, or the normal force, that's in the up direction, and there's 2 in the down direction. So this is actually with gravity now, whereas in number 9, that little piece of the pull was in the up direction, so it was on the same team as the normal force. That means that the normal force is now going to have to equal both of those together. So that normal force on the block from the ground, just going to keep calling that different things. So if this was 2 and this was 5, this would have to be 7, for example. So we could write an equation very easily for that. It'd just be like this plus this equals this. And we'll do stuff like that soon enough. If it's going at a constant velocity, there must be friction. And in the back and forth direction, there's only this versus this. So they must be equal. Force of friction on the block from the ground. All right. Now, what the heck is this about? Well, this is kind of a different, obviously this is not making force diagrams. Determine the x and y components of each of the force vectors. So if you got this here, if this is 12N, what's that? Those are newtons. We'll talk about that soon. That's the units for force. Talk about exactly what those are, like how much a newton is. So this is like in one of these problems, if you were actually going to try to do something here with numbers, and you knew that that was 60 degrees, and you wanted to find the x and the y components of this, could you do that? Well, you used to be able to do that when you were in geometry class. I wonder, can you still? So let's see. Do you remember your SOHCAHTOA? Some old hippie caught another hippie tripping on acid, or if you want a more grade school version of it, some old horse caught another horse taking oats away. Different teachers have different little mnemonic devices for remembering that. Like the old teachers who were like around in the 60s, that's a little older than me. They probably do this some old hippie thing because they're a bunch of old hippies themselves. When I was in school learning this, we just learned it as SOHCAHTOA. We just said SOHCAHTOA, and we didn't actually have any words that they stood for. So whatever works for you. Of course, it doesn't work at all if you don't know what these letters stand for. Some old hippie, no, actually, no, what they really stand for is sine is opposite over hypotenuse. So the sine of 60 is equal to opposite over hypotenuse, which means that the y, this right here, is going to be equal to 12 times the sine of 60. So 12 sine 60, about 10.4. And I'm just going to put it right in the picture there, and the newtons, whatever that is. And then here, if you do the same thing, but with an x here, because we would be doing adjacent over hypotenuse, then that means x is equal to 12 times the cosine of 60. And of course, the cosine of 60 is a half, so there you go. All right. So how about this? That's 15 newtons, and this is 20 degrees. So the x-coordinate is going to be equal to 15 times the cosine of 20. You remember from pre-calc that cosine goes with x, so that's the same deal for us, and this is going to be 15 times the sine of 20. So let's see, 15 cosine 20 and 15 sine 20. Why are we doing this? Why is this trig happening all of a sudden? Well, if we want to be able to do this kind of stuff, like eventually we're going to need numbers for these pieces so we can figure out what's equal to what. So that's why we're doing this. You probably saw that. I mean, you knew that. Who am I talking to? You guys are smart. You guys know what's up. All right, so here, this is 10, and this is a 15-degree angle, 10 newtons. So 10 times the cosine of, what was the angle? 15? 15, and 10 times the sine of 15. So it looks like we got 9.7 and 2.6. 9.7 and 2.6. If you're wondering, wait, how come you're not putting a negative sign on that? Because that's going like into this quadrant. Well, I guess that kind of makes it negative if you're doing things like that in math class. For us in our force diagrams, we just want to have numbers and then have the arrows that they're next to help us understand what direction, right? So if this was like 7, for example, I wouldn't write negative 7 here. It's like 7 the other way, which balances. So we'll do more quantitative stuff soon. No free pizza today, sorry.